Hi, my name is Arun, and in this video I'll be going over our recent paper, Universal Algorithms for Clustering Problems, and this talk is based on joint work with Bruce Maggs and Debmalya Panigrahi. So let's start by recalling the standard notion of a clustering problem. So in a clustering problem, we're given clients C and facilities F that lie together on symmetric space, and our goal is to choose K of the facilities in F. We'll denote the set of facilities we choose S. So we think of it as we open those facilities, and then each client pays its connection cost to the closest facility. And our goal is to minimize some function of these distances or connection costs. So for example, some standard functions that might get used are the k-median objective. So for the k-median problem, the function would just be the sum of the distances. Or for example, you might have k-means. So in k-means, the goal is to minimize the L2 norm of the vector of distances. Or you might have the k-center problem, where the goal is to minimize the maximum distance. Okay, so cluster problems obviously have a variety of applications, some of which I've listed here. And something that in practice is common for all of these is there's some amount of uncertainty actually in the set of clients that appear. So for example, in this snippet from a website on advice for using Google's AdWords services, it points out that you can sort of bid to try to advertise to certain demographics, but there are a lot of AdWords users who have various parts of their demographic identity not specified in the system. And so when you're seeing the set of potential clients that you might be advertising to, you don't have total certainty about what the full set of clients actually is. Another example, which was one of the main motivations for this line of work, is when placing servers for a content delivery network. We don't actually know ahead of time the set of users that are going to be using our content delivery network. And so we need to choose a set of server placements that is fairly robust to all the possible ways that a set of clients could actually appear. So we can see there's sort of this mismatch between standard theoretical notions of clustering problems where you know the set of clients in advance, and these actual practical problems where there's some uncertainty in the set of clients. And so there are various approaches we can take to handling uncertainty, and I'll discuss a few of them here. So one very simple one is to just assume we have some perfect information about what the set of clients is. And theoretically, this makes the problem very easy, and we have all sorts of great approximation algorithms and heuristic algorithms for these problems. But this assumption may be poor in practice, and so we might end up with a solution that's very good for what our predicted set of clients was, but is very poor for the set of clients that appears in reality. So to alleviate this assumption a bit, we might, for example, predict a distribution on the clients, and then maybe try to find a solution that has low expected cost or low variance in cost on this set of, or on this distribution of clients. However, even if such an algorithm existed, we still kind of run into this problem that predicting a distribution on the clients isn't that much easier than just predicting the actual set of clients that will appear itself. So both of these require a lot of cost in just obtaining the input to the problem. So a more robust notion, and one that was popular around a decade ago in the theory community, is the idea of universal algorithms. So universal algorithms, we basically try to simultaneously, or find a solution that simultaneously approximates the optimal solution for every set of inputs possible. So the upside here is that these results are very robust in practice because the guarantee is designed to be a robust one. And it doesn't really require you to do a lot of user research, for example, to figure out what the possible, to figure out what your input is. You just have to come up with a possible set of inputs that you would like to be robust to. But then, unlike the previous two, sort of the theoretical situation is a bit harder, and we don't really know whether good algorithms exist for these kinds of problems. So let's go into what a universal algorithm is more formally. So in a universal algorithm, we have some sort of covering problem. So we want to cover the elements in S, and the idea is we're going to choose a way to cover each element such that for any subset S prime of these elements that could appear, the covering for S prime is an approximation of the optimal covering for just that subset. So maybe to make this more concrete and easy to understand, let's consider one of the more famous universal algorithm problems, which is universal set cover. So in universal set cover, we're given the elements X and then the sets that can cover these elements S1 to Sm. And our solution is going to be a map from each element to one of the sets covering it. Okay, and then we'll evaluate how good our solution is by the approximation ratio, which is defined as we look at the maximum over all possible subsets of the elements X, and we look at the ratio of the cost of the sets that we map these elements to over the cost of the optimal solution for these sets. So again, to be clear, here we're sort of only paying for the sets that have elements that appeared mapped to them. And you can see sort of from this definition that if we have a small approximation ratio, then that in some sense means that this map F is good for every possible input in this universe. So as I was saying in the previous slide, if we could get some very good approximation for universal set cover, then this would be very robust and useful in practice. But it turns out that we understand the problem pretty well, and this isn't really possible. You can't really get good approximations. So we know how to get a roughly square root n approximation for universal set cover, and we know this is also essentially the best possible. Now, it's important to point out here that this is a very poor approximation ratio, but in some sense, this isn't because universal set cover is a very algorithmically hard problem, because again, we're getting an approximation ratio that nearly matches the lower bound. So this approximation ratio isn't poor because of the algorithmic complexity of the problem, but because the problem just has a lot of uncertainty baked in, and the definition of approximation doesn't allow any slack based on how uncertain the instance is. Okay, so going back to clustering algorithms, and in particular for this talk, I'll mostly focus on k-median. We can consider the universal k-median problem. So in this problem, we're given a set of clients C, and we want to find a solution S that is good for all possible subsets C prime of C. So in particular, we could define the approximation ratio for this problem to be the maximum over all C prime of the cost of connecting the clients in C prime to our facilities S divided by the optimal cost of connecting clients in C prime to the facilities. And the natural question is, what approximation ratios can we get for universal k-median in the worst case? And as it turns out, the answer is we can't even get a finite approximation ratio. So to see why that is, let's consider this instance. So throughout this talk, when I draw instances of k-median or other clustering problems, I'll use squares to represent facilities and circles to represent clients. So let's say we have just 4 clients and 4 facilities. Each client is co-located with a facility. That is, it has some facility distance 0 from it. So there's 4 points in this metric, really. And then these 4 points are on a uniform metric. So effectively, every client is distance 0 from some facility, and then distance 1 from all the other facilities. Okay, and let's say here we're solving 3 medians, so we can pick 3 of the 4 facilities to open. So let's say we choose these 3, because it's a uniform metric, so we can just kind of pick any 3, and it'll be as good as picking any other 3 facilities. So naturally, the set of clients that is going to maximize the approximation ratio for the solution is going to just be to include this one client in the bottom right that isn't distance 0 from any of our facilities. Okay, so our algorithm is going to pay cost 1 because it's distance 1 from its client because it didn't buy the facility co-located with the client. But the optimal cost is of course 0 because we could have just picked the facility located at this client, and there's no other clients to worry about in this instance. So in this case, our approximation ratio is infinite. And again, this is as good as we can do for this instance because basically every solution is more or less equivalent to every other solution. So what this sort of tells us is that if we really want to understand these problems and get useful theoretical results, we can't have this approximation definition that doesn't allow more slack based on the uncertainty in the instance. We need to bake the inherent uncertainty in the instance into the approximation definition. So one model that has been studied extensively in the operations research community and that does actually bake the notion of uncertainty into the definition of approximation is a regret minimization model. So in the regret minimization model, if we're given a solution, we can define its regret to be the maximum of all possible subsets of clients of the additive difference between the cost of the solution and the cost of the optimal solution for that set of clients. So in particular, let's denote the smallest possible regret of any solution by MR, or the minimum regret, and then we'll let MRS denote the solution that actually achieves the minimum regret. So for example, let's say I have this clustering instance. Again, the squares on the top are facilities and the clients on the bottom are potential clients. And let's say I'm allowed to pick 2 of the facilities. So let's say I pick these 2 facilities. Then the realization that's going to maximize my regret is going to be the one where only this middle client appears, and opt picks the 2 facilities with red borders. So in this case, my algorithm has distance 4 from this client, whereas opt only has distance 2 from this client. And so the regret of my solution is 2. However, I could have instead picked this solution with the top left and top left and top right facility. And in this case, the worst realization for me is going to be when only the rightmost client appears, and opt takes, say, the left 2 facilities as its solution. So in this case, I'm distance 3 from this client, but opt is distance 2, so I only pay a regret of 1 here. And actually, in this case, the solution I chose is the minimum regret solution. So again, recall that we let MR denote the minimum regret that any solution can obtain in the instance. And so a natural question is it possible to obtain a solution that has regret, say, some constant times MR, in particular in polytime? It turns out the answer is no, and the reason is that if we consider set cover-like instances, and by that I mean effectively facilities are sets, clients are elements, and then facilities are close to clients that are in this, that correspond to elements in the set they represent, and are far from the elements not in the set that they represent. So in these instances, it turns out you can construct them such that there's a zero regret solution if there's a set cover of size k, and any set of k facilities that doesn't correspond to a set cover is going to have some positive regrets. So again, it's not possible to get any finite approximation of regret in general in polynomial time. So the takeaway here is, now this definition of regret and approximating regret bakes in uncertainty into the approximation definition, but it's still not sufficient just to approximate this. So it's not sufficient to approximate opt, it's not sufficient to approximate the regret. We need to really approximate both if we want any meaningful guarantees. Okay, so now I'll introduce a definition of approximation that allows us both the approximation on the optimal solutions cost and also the regret. So I'll say the solution S is an alpha beta approximation if the maximum difference between the cost of the solution and alpha times opt is at most beta times the minimum regret. One way you can rewrite this is to say that in every realization, our solution's cost is at most alpha times the optimal solution's cost plus beta times the minimum regret. Okay, and the main result of our paper is that universal k-median and various other problems, but I'll focus on universal k-median for this talk, has constant approximation algorithms. And furthermore, we show that even if we allow alpha to be arbitrarily large, then beta has to be at least 2, and even if we allow beta to be arbitrarily large, alpha has to be at least 3. So this just further reinforces what I was discussing on the previous slide, that alpha-beta approximation is in some sense the strongest notion of approximation that we can get away with in this setting. So before I move on to the technical part of the talk, I just want to motivate why this problem is technically interesting. So one natural approach would just be to try to reduce universal k-median to the classical setting of, so just classic k-median. And if we could do this, then your life would be very good because we understand the classic k-median problem very well. And one reason we might hope to do this is what's been well known for a while, is that if I take the instance where all the clients appear and I find its optimal solution, that solution is actually a 2 approximation of the minimum regrets. Of course, k-median in general is NP hard, and so we can only really try to approximate the solution for this instance. So natural question then is, if I just run some generic approximation algorithm on this instance, do I get a solution with good regret guarantees? And it turns out the answer is no, and the reason this is that approximation is a very global guarantee. So an approximate solution might do much worse than the optimal solution for a certain subset of clients, and that means sort of in the realization where only those clients appear, I'm pretty screwed. So to make this more concrete, consider this instance where I have 2 facilities and 2 clients. So both facilities are distance 1 from the left client, and then one facility is distance 0 from the right client, whereas the other facility is distance epsilon. Now suppose I'm solving universal 1 k-median here, and I run a even 1 plus epsilon approximation algorithm for the instance where both C1 and C2 are clients that I have to pay for. So my 1 plus epsilon approximation algorithm could feasibly only pick F2. Now, picking F2 doesn't get me a good regret solution because in the realization where only C2 appears, opt is 0, and picking F1 has regrets 0 because you can never do better than picking F1 in any realization. So opt is 0, and then minimum regret is 0, but my solution that picked F2 has to pay epsilon when C2 appears. So for any finite alpha or beta, the solution doesn't get the alpha beta approximation guarantee. So this says we really need to do something more interesting and that really uses this problem's unique properties rather than just reduce to classic k-median. Okay, so in the rest of the talk, I'll just give a quick technical overview of our results, and I'll just focus on solving universal k-median. So I'll discuss solving and rounding an LP for it, and then at the end, I'll just briefly go over some of the extensions in the paper, but I'll leave it to you to read the paper for the technical details there if you're interested. Okay, so let's just start with solving the LP for universal k-median. So to write the LP for universal k-median, we're just going to start with the standard k-median polytope. I assume most of you are probably at least somewhat familiar. If not, the details aren't too important. The main thing is just to know that we can write the objective as some function of these variables y and then the client c. And then we're just going to refer to the rest of the constraints as the polytope p. So this is standard k-median LP. And now for the regret minimization LP, I'm going to say that I want to minimize R, subject to the variables xy that appeared in the classic LP being in the polytope P. And this constraint is very easy to separate. But I'm also going to have this constraint that for every subset of clients C prime, the difference between the cost of the fractional solution on C prime and the optimal cost for C prime is at most R. So here R represents the regret, and my goal is just to ensure that this regret bound holds for every realization. So effectively separating this last set of constraints is equivalent to determining the regret of the fractional solution given by x and y. So to solve this LP, just by the ellipsoid method, we can reduce to computing the regret of the fractional solution. But in general, the computing the regret of any solution is NP hard. So instead, we're going to settle for approximately computing regrets. And this is enough because if we can approximate the regret of the fractional solution up to a factor of beta, then we can basically just run ellipsoid using this approximate separation oracle, and we'll get a 1 beta approximate fractional solution, which is enough for our final guarantee. Okay, so our goal is to approximately compute the regret, which again, we can just write as maximum over all subsets of clients of the difference between the cost of the fractional solution and opt. And since opt is just the best of all the possible solutions, we can really just rewrite this as we're computing the maximum overall solutions of the maximum overall subsets of clients of the difference of the cost between the fractional solution and the solution S we chose. And this is it's useful to rewrite this way, because given S, it's very easy to choose the C prime that maximizes this expression. Because effectively, if we want to maximize the difference between the cost of the fractional solution and the solution using facilities S, we should only include a client if it's cheaper for S to cover that client than it is for the fractional solution. So if we're given S, we can pretty easily compute the maximizing C prime, and thus we really just need to find the best choice of S. And it turns out this is not that hard to do, approximately, because we can show that this difference in costs is actually a monotone submodular function of S. So approximately computing the regret just by this chain of logic can be reduced to submodular maximization under a cardinality constraint. Okay, so just to recap, our method for solving the LP was to realize that we only really needed to separate the constraints corresponding to regret, which just required us to approximately compute the regret of the fractional solution, and then we showed that that was just an instance of submodular maximization. So now let's talk about how to round the LP once we have this fractional solution. So when we're thinking about how to round, one very natural idea is just to use a black box rounding algorithm from one of the many previous papers on K-median. So it would be nice if this worked, but unfortunately it doesn't. And it's just because of this common issue that's appearing again and again throughout this talk, which is that these roundings give a very global guarantee. That is, they say the average client's connection cost doesn't blow up by too much. However, it's possible that there are some small subset of clients whose connection costs blow up by a very large factor. And so these roundings aren't going to give us any meaningful guarantees in the realization where only those clients appear. And this isn't just an algorithmic hardness issue, this is actually an information theoretic issue. In general, for K-median, any rounding has to blow up some client's cost by on the order of K in the worst case. And just to give you an example that demonstrates this is true, again, consider this 4 facility, 4 client instance on a uniform metric. So every client is distance 0 from the facility at the same point, and then distance 1 from the 3 clients not at the same point. And I'm discussing a 4 facility, 4 client instance here, but you should really think of this as a K plus 1 clients and K plus 1 facilities. So I can, in my fractional solution, pay for fraction K over K plus 1 of every facility, and then connect each client to that K over K plus 1 fraction of the facility at the same point. And then for the remainder of its connection cost, I'll just connect it to one of the other clients that's distance 1 away. So fractionally, every client is going to have connection 1 over K plus 1. However, in any rounding, I'm going to have to choose some location not to place a facility at, and the client at that location is going to have connection cost 1 instead of 1 over K plus 1. So in any rounding, some client's connection cost will get blown up by this K plus 1 factor. So what the example in the previous slide demonstrates is that we can't hope for some pure multiplicative per client rounding guarantee. So the natural next question to ask is it possible to get some multiplicative rounding guarantee with some additive slack? So it turns out this is possible, and in particular, let me describe the form of the guarantee we'll aim for. So let Fj be the fractional connection costs for client J, and then let Cj be the rounded solutions connection costs. So it suffices if basically the sum over all the clients of the maximum of the difference between Cj and some constant times Fj, or 0, is at most some constant times Mr. And why is this efficient? Well, if we massage the above inequality, we can get that for any realization C prime. The cost of the rounded solution in that C prime is at most some constant times the cost of the fractional solution plus some constant times the minimum regrets. And so if the fractional solution is an alpha beta approximation, then the rounded solution is also going to be an alpha beta approximation for some larger values of alpha and beta. So this is efficient, but why should we expect this to be feasible? Well, because k-median has an integrality gap of 3, we know that if we replace this 3 times fj with basically the cost of the optimal solution's connection cost, then this can only increase the quantity or the value of the sum. So that is to say, this integrality gap bound tells us that the regret of the rounded solution versus 3 times the fractional solution is always going to be at most the regret of the rounded solution versus opt. And in particular, if we plug in the minimum regret solution, which we know has regret at most MR against opt, we find that the minimum regret solution is a certificate that there is some integral solution whose regret against 3 times the fractional solution is also at most MR. Okay, so the minimum regret solution provides us a certificate that this type of guarantee is achievable by some integral solution, but we still haven't talked about how to actually find a solution that gets this form of guarantee. So to do this, we're going to introduce a new problem called k-median with discounts. In k-median with discounts, for each client, we'll have a discount rj. And now, rather than the cost for that client being the connection cost cj, the cost for that client is the max of cj minus rj, or 0. That is, we get a discount of up to rj on each client's connection cost, but then past that discount, we still have to pay for its connection cost. So it turns out if we just modify the standard k-median primal dual algorithm, then we get a result that says if we use discounts that are 9 times as large as the discounts we were given in the problem, we can get a solution with cost at most 6 times opt using the original discounts. And this turns out to be enough to get the previous guarantee we're looking for. So this gives us our final rounding algorithm, which is to set the discounts to be 3 times the cost of the fractional solution's connection costs, and then use this approximation algorithm solution as our rounded solution. And again, in the analysis, we'll just use the fact that MRS certifies some low-cost solution to the k-median with discounts problem. Okay, so this wraps up our discussion of universal k-median. However, in the paper, we consider many more problems that are extensions of universal k-median. So I don't have much time left, but let me just briefly go over the extensions and the challenges that come up in addressing them. So the first extension we consider is when the cost function is not the k-median objective, but more generally the LP norm of the connection costs. So the first challenge that arises is even for something like k-means, if we're given a fractional solution in S, it's not clear how to compute the set of clients that maximizes the regret of Y with respect to S. And this is because when we move on to, say, the L2 objective, it turns out that sometimes adding a client that is closer to S than to Y actually decreases the regrets. And this happens in a very non-submodular way. So the previous claim we had that this regret is some submodular function given by just obviously choosing the set of clients is no longer true. The second challenge that arises is that k-median with discounts is a very cleanly defined problem, but k-means with discounts, it's not as clear how to define it. For example, should we be taking the L2 norm of this max cj minus rj, or should we be taking max of cj minus rj to the squared, etc.? So it turns out that the right thing to do is actually to use L2 squared clustering. So the objective is the k-means objective squared. And this goes back to being a linear objective. But then we have to relate the regret in the L2 and L2 squared objectives, which is somewhat non-trivial. So the second extension we consider is when we're told there's a set of fixed clients CF, such that we only need to worry about the realizations that are supersets of CF. So the first challenge is that since some clients are always forced to appear, it's actually possible to have a fractional solution with negative regret, and more generally, the function we had earlier that we claimed was submodular is no longer non-negative. So this kind of makes the approximation guarantees very useless, because if the function is very non-negative, then the approximation doesn't really tell us anything. So the second challenge that comes up is that we have to set the discounts in k-median to account for fixed clients, since there's a disparity between the fixed clients and the rest of the clients. Okay, just to briefly conclude some interesting future directions. So one is that the constants in our approximation ratios are much larger than what we get classically. So a natural direction is to try to improve our results so that we get constants more similar to what we get in the classic setting. Another interesting direction is whether we can get better constants if we were allowed to use more than k facilities, say k log n facilities, since our lower bounds no longer hold in that case. And finally, We know that we can get a 2 approximation for universal k-median in metrics like tree metrics and line metrics, but it would be interesting to see if we can do better than 2. All right. Thank you for watching, and I'd be very happy to answer questions offline or in the rest of the conference.